Hi everyone, my name is Manel Rodríguez-Soto. I'm a PhD student at IIIA at Barcelona, and now I'm going to present you the paper that I have written together with my supervisors, Maite Lopez-Sanchez and Juan Rodríguez-Aguilar. And we have called this paper Guaranteeing the Learning of Ethical Behavior through Multi-Objective Reinforcement Learning. So, to begin with, we all have seen how the current advancements in AI are showing very impressive results each year. So every year they are capable of dealing with more complex tasks and being more integrated within human societies. However, in order for them to fully integrate in human societies, we need to guarantee that agents learn to behave ethically, that is, in alignment with moral values. And this well-known problem in the artificial intelligence community has received the name of the value alignment problem. A common approach to tackle it is to apply reinforcement learning so the agent learns what is ethical and what is not by trial and error. In more detail, this approach consists in designing an environment that incentivizes ethical behaviors or penalizes unethical behaviors by means of some exogenous reward function. The problem is that these incentives are chosen with a lack of theoretical guarantees. So we cannot know for certain if the agent will learn to behave ethically or not. So this is our research question. How can we guarantee that the agent learns to behave ethically while still pursuing its individual objective? And before we continue, let me show you a running example that I will be using to illustrate the concepts of the paper. This example is called the public civility game, and in it, two agents need to move every day through an arrow path to their destination. And while there are two agents in this example, only the one at the left needs to learn its policy, so the one at the left is the learning agent. So we can express the individual objective of the agents as getting to the goal as fast as possible. But as we can see on the picture, the left agent, which is the only learning agent, finds a piece of garbage in its way. So in order to promote a more civic society, we would like the agent to act in accordance to the moral value of civility and bring this piece of garbage to a bin. So we can express the ethical objective of the agent as civility. For this example, we will assume that the learning agent can perform three kinds of actions. First, move towards the goal, then second, throw the garbage aside, which could hit the other agent, and third, bring the garbage to a bin. Each action has different consequences with respect to the two objectives, the individual and the ethical objectives. So the action of throwing the garbage aside promotes the individual objective since it allows the agent to get faster to its goal. But it demotes civility because it creates a dirtier or even a dangerous society if the agent throws the piece of garbage to where the other agent is. Conversely, the action of bringing the garbage to a bin demotes the individual objective because it is the slowest option of the two. But it is also the best option of the two in terms of promoting civility because it guarantees a clean and safe street. This leads us to the following conclusion, that the public civility game is a natural instance of a multi-objective decision-making problem. So, in more detail, in order that the agent learns to behave ethically, the first step is to properly model its learning environment as a multi-objective one with two objectives, the individual objective and the ethical objective. We call this process the reward specification process. This way, we can aggregate the two rewards in a way that prioritizes the ethical objective to the individual one. And we give this second process the name of the ethical embedding process. Then, if the agent learns in an environment with such ethical embedding, it will learn a behavior, a policy, that prioritizes its ethical objective to its individual one. Also notice that by making this new ethical environment a single objective environment, we are simplifying the learning process of the agent. So let me quickly emphasize on this. The agent's only work is to learn in the ethical single objective environment. On the other hand, the two aforementioned processes, reward specification and ethical embedding, are the task of the environment designer, that is, us. Also, in this work, we assume that the reward specification is already done, and we only focus on tackling the second step, the ethical embedding process. Alright, so in summary, our approach consists in designing an ethical environment that guarantees that the agent learns to behave ethically while still pursuing its individual objective. More in detail, we provide our solution by means of the following two contributions. First, we provide the theoretical means to design a learning environment wherein ethical behavior is guaranteed. And then, we also provide an algorithm for automating the configuration of the learning environment. Now, I will start by explaining the first point, the theoretical means. Here, the first step is to formalize the ethical embedding problem. And to do so, we start by modeling the individual objective and the ethical objective of an agent as two reward functions of a multi-objective Markov decision process. So we will refer to this particular kind of multi-objective MDP as an ethical MOMDP. Furthermore, based on the ethics literature, we give more structure to the ethical reward function and we divide it in two equally important components. First, a normative component that penalizes the violation of ethical requirements, and second, an evaluative component that rewards the performance of praiseworthy actions. With this, an ethical MOMDP has the following structure: an individual reward function R0 and an ethical reward function Rn plus Re. And before we continue, in case any of you is not familiar with multi-objective Markov decision processes, so here you have the definition. They are simply a generalization of MDPs that instead of having a single reward function, they have a vector of rewards. And consequently, the value function of a MOMDP is also expressed as a vector. And these are all the differences with respect to single objective MDPs. Back again with ethical MOMDPs. Having defined them, we can also formalize the concept of an ethical policy. We define an ethical policy as any policy of an ethical MOMDP that maximizes both the normative and the evaluative reward components. Here at the right, you can see a Venn diagram showing how the ethical policies are, of course, a subset of all policies. And while this definition is very helpful, we still need more. As I have mentioned, we want the agent to behave ethically while still pursuing its individual objective. And this definition says nothing about the individual objective. So for that reason, we define an important subset of ethical policies, which we call ethical optimal policies. An ethical optimal policy is the ethical policy that fulfills the most its individual objective. And as you can see at the Venn diagram at the right, ethical optimal policies are a subset of all ethical policies. Ethical optimal policies are the kind of policies that the agent should learn. But how can we create an ethical environment in which the agent learns an ethical optimal policy? So recall that we wanted to create a single objective environment in which the agent would learn its policy. And for that, the classical option in multi-objective reinforcement learning is to use a scalarization function. As its name implies, a scalarization function transforms the vectorial rewards of a multi-objective environment into the scalar rewards of a single objective environment. The most typical option is to apply a linear scalarization function that computes a weighted sum of the different objectives. So, for instance, in the case of ethical MMDPs, this is how a linear escalarization function would look like. A weighted sum of the individual and the ethical objectives. Here, W0 is called the individual weight, and WE is called the ethical weight. In this work, we also consider a linear escalarization function in order to design the ethical single objective environment. In our case, also, for simplicity, we fixed the individual weight. And therefore, the work of the environment designer, that is, us, will essentially consist on setting the appropriate ethical weight for the escalarization function that creates the desired ethical environment. And we now have all the theoretical means to formalize the ethical embedding problem as follows. So, given an ethical MOMDP, how do we need to set the ethical weight of the ethical embedding in order to guarantee that in the design single objective MDP, all optimal policies are ethical optimal. So this is the ethical embedding problem. And here you have a graphical representation of the problem with Venn diagrams. At the left, you have the subset of ethical optimal policies of an ethical MMDP. And what we want to do is to design an ethical embedding that guarantees that this set of optimal policies in the single objective environment corresponds with the set of the ethical optimal policies. Moreover, we assume that incentivizing the agent to behave ethically has a cost for the environment designer, for us. And for that reason, we want to obtain the minimal value of the ethical weight that allows the ethical embedding. So now we proceed by first studying the solvability of the problem. That is, we study under which assumptions we can obtain this ethical weight. In this work, we have proven that the only necessary condition that we need to assume is the following one: that there exists at least one ethical policy in an ethical MOMDP. In plain words, what this existence condition tells us is that if we want the agent to behave ethically, it must be possible for it to behave ethically. With this condition, we can prove the following existence theorem, which is also one of the main results of our work. So, given an ethical MDP, there exists an ethical weight for which all optimal policies are ethical optimal, which means that every ethical embedding problem is solvable. We do not have time here to show you the proof of this theorem, but you can find it in full detail in our paper. So, with these results, we can finally proceed to solve the ethical embedding problem. Our proposal to solve it is a three-step algorithm that obtains the desired ethical environment in which the agent learns to behave ethically. And as mentioned before, our algorithm consists in designing an ethical environment directly from computing the appropriate minimal ethical weight. The main concept for computing our solution is the computation of the convex hull of an MOMDP. And for those unfamiliar with the term, the convex hull is defined as the set of policies and their associated value vectors that are optimal for some weight vector. So we start with the first step, and as you can imagine, it consists on computing the convex hull of the ethical MOMDP. But not all of it, we only need to compute a partial subset of the convex hull. In more detail, we want to compute the partial subset that contains the ethical optimal policy and its associated value vector. The figure at the right shows the example of the partial convex hull for the public civility game. These black dots are the policies that form the partial convex hull, represented in objective space. The x-axis shows the value of the policies with respect to the individual objective, and the y-axis shows the values with respect to the ethical objective. The next step that we perform is to find the ethical optimal value vector inside the computed convex hull. In our example, the ethical optimal value vector is the one that we highlight here with this green arrow. Notice that this is the one with the maximum accumulation of ethical rewards. This value vector corresponds to the policy that always brings the garbage to the bin, and after bringing it, it goes as fast as possible to its destination. The reason why we identify this precise value vector is because it will serve us to compute the desired minimal ethical weight. And here is the relationship between the two concepts. For any value higher than this ethical weight, the ethical optimal value vector will be the only optimal one. But how do we exactly determine this value? The good news is that we do not need to consider all the value vectors on the partial convex hull in order to compute the minimal ethical weight. In fact, we only need to also identify the second best value vector in terms of ethical rewards. In the case of the public civility game, this second best value vector is the one that we highlight here with the orange arrow. So you can see that it is the one that accumulates the greatest amount of ethical rewards after the ethical optimal one. With these two value vectors identified, it is direct to find the value of the ethical weight, because it is the point at which they intersect in weight space. Here you have the figure of the convex hull in weight space highlighting the two value vectors. Here the x-axis is the value of the ethical weight, and the y-axis shows the scalarized value of the different policies of the hull. Notice that after the ethical optimal value vector intersects with the second best one, the ethical optimal value vector becomes the only optimal one. So, in summary, our three-step algorithm consists in first computing the partial convex hull P of an ethical MOMDP, then extracting the ethical optimal and second best value vectors from the partial convex hull, and finally obtaining the minimal ethical weight WE by computing where the two value vectors intersect. After computing this ethical weight, what we do now is setting the escalation function with the computed value, and we can finally use it to produce the desired ethical embedding, obtaining a single objective ethical MDP. And we would like to remark that this is an exact process. It is guaranteed that in this ethical MDP, all optimal policies will be ethical optimal. So, back to the public civility game example, we created the ethical environment following this algorithm. And afterwards, we have made the agent learn with a single objective reinforcement learning algorithm, Q-learning in our case, and we have checked that it effectively learns an ethical optimal policy as expected. Also, the computational cost of the algorithm resides mainly in computing the partial convex hull of an multi-objective MDP, and applying an exact algorithm such as convex hull value iteration requires an order linear logarithmic times what its single objective version takes, where here the n corresponds with the number of points in the partial convex hull. To finish, we conclude by summarizing the main contributions of this work. First, we make headway in tackling the problem of designing ethical environments by providing novel formal and algorithmic tools that build upon multi-objective reinforcement learning. Then, we characterize the obtention of an ethical environment as a two-step process that first specifies rewards and second performs an ethical embedding. We proceed by formalizing this last step as the ethical embedding problem, and we theoretically prove that it is always solvable. Finally, our findings lead to an algorithm for automating the design of an ethical environment in which it will be in the best interest of the agent to behave ethically while still pursuing its individual objective. And finally, as to future work, we would like to further examine empirically your algorithm in more complex environments. And this is all. Thank you very much for your attention, and I hope you enjoyed this presentation. Bye.